Welcome back to Differential Equations. In this video, I'm going to talk a little bit about mixing tanks. I normally don't devote an entire video just to a specific application, but in this case, I think it's warranted. First of all, the idea of mixing tanks has been the established standard of the application of first-order differential equations for literally hundreds of years at this point. Some of the earliest textbooks in differential equations written by the names that you learn about in a course in differential equations started using mixing tanks as their examples. So there is historical context as to why this is how we want to approach things. Mixing tanks are not something that most people see in their everyday life, but it is something that is very easy to grasp and gives a pretty good understanding of some of the applications we can use our first order equations for. So that's the way I like to approach this. No, for most of you, for some of you, you will see this. If you're going into chemical engineering or mechanical engineering or civil engineering, there is a chance that the idea of a mixing tank is going to be something you see again. But for most of you, this is not going to be a tool that you use regularly. But again, it is a fairly easy to grasp concept. And once you understand the concept, I hope that it helps you look at the particular field of study you want to continue onward to and see how these problems are going to fit into the later use cases. Let me get my head out of the way and let's start drawing some bad pictures. The first thing that I need in order to talk about the mixing tank problem is a vat. All right, so there is my large vat or tank. The second thing that I need in my mixing tank problem is some source. Let's draw that a little bit higher. Right? I need something to be pouring into my vat. The third thing that I need is a drain. I need things to be pouring out of my vat. All right. So we're going to call it water. Water is pouring into this vat at some rate, which we will call R sub in. Water is also pouring out of this vat at some rate we are going to call R sub out. A couple of very obvious things that you should see in this picture. If R in is larger than R out, then the water level in the vat is going to rise. If R in is smaller than R out, then the water level in the tank is going to drop. I think that's pretty obvious. I don't want to deal with that happening, so I'm going to specify here that the rate at which water is going into the tank and the rate at which water is leaving the tank are going to be the exact same rate. That way, the water level stays perfectly even. The thing that I want to think about in this problem is I'm going to assume that the water that I'm dealing with is not pure water. For the sake of something to think about, I'm going to call it salt water. I'm going to assume that the water coming into the tank is road runoff on a wintry day where there is road salt mixed in with the melted water that is falling into the drains. And then that water comes into the tank and it pours out. Not because we want it to pour out. This is a bad illustration. Instead, I want to look at the case of the tank is overflowing. Drain runoff is pouring into the tank, and the tank is full all the way to the top of the tank. So any bit of water that enters the tank, that same amount of water is immediately leaving the tank. With that, we can start looking at how does the concentration of salt change over the course of this process. The water coming into the tank is salty. Maybe the water in the tank was originally saltier than the water that's coming in, or maybe the water in the tank was originally less salty than the water that is coming in. Or maybe the water in the tank is very salty and the water coming in is clean. Given those conditions, and with the assumption that the water in the tank is constantly mixed so that the concentration of salt in the tank is uniform, which is a bad assumption, but it will make the math a lot easier. Now we want to think about how much salt is leaving the tank, right? Not necessarily how much water, because we can figure that out based on how much water is going in. But if we know how salty the water going into the tank is, and we know how salty the tank was in the first place, how much salt leaves the tank with all of the water that leaves the tank? Those are the kinds of questions that we want to ask in this lesson. Let me get my head out of the way and let's look at a particular example. Consider a 300-gallon tank of water into which we have dissolved 50 pounds of salt. We have our pipe pumping in water. The water is coming in at 3 gallons per minute, and the water coming in has a 2 pound per gallon salt concentration. As I said earlier, we're going to assume that the water coming in is mixed thoroughly, and then it is overflowing from the tank at the same rate at which it's coming in. So the volume of water in the tank remains 300 gallons throughout the entire process. For this problem, we're going to specifically ask how many pounds of salt are dissolved in the tank after 60 minutes are up. For practical purposes, this is generally not the kind of question that we are interested in asking for a problem like this, but it certainly is a question that we can ask. We'll generally be looking for things like find the expression of the amount of salt leaving the tank per unit time, or the concentration over time, which is going to vary, right? The concentration coming into the tank is constant. The concentration leaving the tank is going to vary. The setup is all the same. The process is mostly the same. This is going to give us a good feel for how this problem is supposed to work, or how problems like this are supposed to work. Right. Unfortunately, the problem fills up the entire page, so I have to move onward and scroll it off the page in order to solve it. But that's okay, we can still manage. So let's define a function capital N of t as the amount of salt which is in the tank at our time t. It's also going to be worthwhile to think about R in, the rate at which salt, not water, not a mixture, the rate at which the salt enters the tank is going to be R in, and then R out is going to be the rate at which salt leaves the tank. And I think that it is fairly simple to think about the relation here. If n of t is the amount of salt, then n prime of t is the rate at which the amount is changing. And there are two ways for the amount of salt in the tank to change. We can add salt, or we can have salt leave. So if we take the difference of the rate at which salt is entering minus the rate at which salt is leaving, that's going to give us n prime of t. Right? In theory, that's a differential equation. All we have to do is try to figure out what R in and R out actually look like. The rate at which salt is entering is pretty straightforward. Water is coming in at 3 gallons per minute, and that water has a concentration of 2 pounds per gallon of salt. The gallons cancel each other out. 3 times 2 is 6. And we get that the rate at which water is, or the rate at which salt is entering the tank is 6 pounds per minute. The rate at which salt is leaving the tank is a little bit more cumbersome, but still relatively approachable. Well, again, water is leaving the tank at the same rate, 3 gallons per minute. And the concentration of salt is going to be changing. Well, we know that the amount of salt is n of t, which, based on the units we've been using for everything else, should be measured in pounds. We want pounds per gallon. So if we take the number of pounds and divide by the number of gallons in the tank, which remember was 300, then that's the concentration of salt in the water in the tank. And again, since n is going to be a function, it's going to be not constant. The concentration is also going to be not constant, but the units are still going to cancel out. N of t is measured in pounds. We have pounds over a minute. So I guess that's 1 over 100 n of t. Again, n of t is measured in pounds, so this is pounds per minute. But technically, we're only going to write the units as per minute because the pounds is inside of the variable n. All right, bringing all of this together, we get that n prime is going to be measured in pounds per minute, and it's going to be the difference of 6 pounds per minute minus n over 100, again, pounds per minute. I can suppress the units because this is math class, not physics class, and we'll just trust that the units are going to work out. And now I have a differential equation. It is, in fact, a first-order linear differential equation, so we can rearrange it so it looks like that. And we can solve by method of integrating factor. Our function is n instead of y, which makes things look a little bit strange, but it still works the same way. Mu prime is going to be equal to the coefficient of the function 1 over 100 times mu. We can solve that separable equation and pick the convenient constant of integration to get that mu itself is e to the 1 over 100 times t. We can use that to rewrite our differential equation as d over dt times n, e to the 1 over 100 times t is equal to the right-hand side, in this case 6, times mu, e to the 1 over 100 t. Integrate both sides. And divide both sides by e to the 1 over 100 t. And we have our general solution. But this time we're not done, because we have one more piece of information that we haven't used yet. If I scroll way up and go back to the original statement of the problem, when we started this tank, before we started pumping water into it, there were 50 pounds of salt dissolved in the water in the tank. We can represent that in the style of our function, if I scroll all the way back down to the bottom here, as the initial condition, n of 0 is equal to 50. Well, if I plug in t equals 0, first of all, why didn't the 5 show up when I said 50? N of 0 is equal to 50. If I plug in t equals 0 into my general solution here, I get n of 0 is equal to 600 minus c times e to the 0, and e to the 0 is just 1. Solving here gives me that c is equal to 550. And now I have my particular solution. N of t is 600 minus 550 times e to the negative 100, or 1 over 100t. And if you think about it, if you play around with it, this should make sense. There I am. First of all, the mathematics of this process. What is 600? Well, if we take that entire 300-gallon tank and we have the entire thing laid out at 2 pounds per gallon concentration of salt, then that means that there's going to be 600 pounds of salt in the tank. We're subtracting something from it. We're subtracting something from it, which is e to a negative times t. That's a decreasing function that's going to have an asymptote. So at t equals 0, we get the full 550. And as t increases, the value of that is going to drop down until infinitely far away. It's going to be 600 minus 0. Right. But I still have one step left to do here, and that is because I specifically asked, what is the concentration of salt going to be after 60 minutes? So I have to plug in t equals 60. So we'll get n of 60 is 600 minus 550 times e to the minus 60 over 100. So let's pop over here. One of the few times I'm actually going to use a calculator in this course. Let's plug that expression in, and my calculator tells me 298.15, etc. Probably 298 is good enough. So to answer our question, there's going to be 298 pounds um, of salt in the tank at the 60-minute mark. All right. Here's a very similar problem for you to try. You can see I've highlighted in yellow the couple of changes from the previous problem. We're still going to be dealing with a 300-gallon tank of water. This time, I'm going to dissolve 100 pounds of salt into the tank to begin with, and then I'm going to start pumping water in using a much larger pump, which is going to get 5 gallons per minute, and the water coming in has 1.5 pounds per gallon of salt concentration. We're still going to mix thoroughly, we're still going to overflow the tank at the same rate, and we're still going to ask the question, how many pounds of salt are dissolved in the tank after 60 minutes? All right. Take a couple of minutes, play around with this one, make sure that it is making sense to you. See where you can get with it, and I'll see you in the next video.